This extremely peculiar piece of precision welded steel looks a bit like a modern art installation, doesn't it? But in fact, it's just one of dozens of similar structures that are linked together to form a computer-designed, millimetre-precise vacuum chamber that allows magnets at a temperature of minus 270 degrees Celsius to get as close as possible to plasma passing through at potentially 100 million degrees Celsius. Now you might fairly reasonably ask, what's the point of that? And it's a fair question. It's part of a mind-bogglingly complex project called Wendelstein 7X, which first entered the design concept stage as far back as 1980. The hope is that by 2021, the fully constructed contraption will be able to achieve a continuous discharge of plasma for about 30 minutes. And plasma discharge is an essential feature of a technology that, if we ever actually manage to achieve it at scale, would solve our energy challenges pretty much forever. And that technology is, of course, nuclear fusion. The incredible complexity of suspending superheated plasma in mid-air and harvesting its energy at an industrial scale without actually touching it means that after many decades of extremely expensive research and development, full-scale nuclear fusion technology remains an elusive prize. But what if there was a way to completely bypass the need to heat up the reactor to temperatures hotter than the centre of the sun? The enormous energy savings could be a game changer. Well, in February 2020, an Australian company linked to a research team at the University of New South Wales announced a swathe of new international patents that claim to have achieved exactly that. So could this be the revolutionary breakthrough in nuclear fusion that we've all been waiting for? Hello and welcome to Just Have a Think. No doubt many of you have heard the cliched phrase that nuclear fusion is just 20 years away and always will be. It's such an unbelievably complex and challenging concept to bring into reality that if it was almost literally anything else, the scientists, engineers and investors would have given up long ago. But nuclear fusion isn't just another interesting technology. It really does offer the possibility of unlimited, risk-free, zero carbon, zero waste energy for the foreseeable future of mankind. And that's a pretty compelling reason to keep persevering despite almost overwhelming odds against success. Nuclear fusion is sort of the opposite of nuclear fission, which is the process that currently drives the world's nuclear power plants. It's the process that's been powering our local star for more than 4,000 million years. The enormous temperatures inside the sun strip atoms of their electrons, and that results in a plasma with atomic nuclei and electrons that are all flying around independently of each other. Atomic nuclei all have a positive charge, which ordinarily means that they repel each other, just like when you try to push the same ends of two magnets together. But the sun is also extremely big. You can fit 1 million Earths inside it. And that enormous mass creates enormous pressure, enough pressure to force those nuclei together, creating heavier elements and releasing really quite mind-boggling amounts of energy in the process. Scientists have been trying to replicate that process on Earth for decades. Arguably the two best funded and most competitive inventions to date are called tokamak and stellarator. They're both examples of what's called magnetic confinement technology. This is the inside of the International Thermonuclear Experimental Reactor, or ITER. It's been in development since 1985 and it's the biggest tokamak machine on the planet at a total of 73 metres or 240 feet in height. It's basically a bunch of incredibly strong magnets that contain a huge donut-shaped stream of hydrogen plasma. The plasma gets compressed by the magnets until the nuclei fuse together and release their energy. But getting plasma up to that required temperature and keeping the streams of plasma in place long enough for the reactions to take place is extremely challenging, and one of the main reasons why the technology hasn't yet come to fruition. There are other tokamak devices being developed around the world, including a UK firm called Tokamak Energy that achieved a plasma temperature of 15 million degrees in 2018, and another device in China called the Experimental Advanced Superconducting Tokamak, or EAST, which since 2016 has been capable of reaching the elusive 100 million degree target, albeit for a very fleeting amount of time. Stellarator reactors fall under the same category as tokamak devices, but these things represent magnetic containment technology with a twist. Quite literally, that big chunk of hardware I was standing in at the start of the video forms just one element of this machine. If we open it up, you can see the weird twisty shape of its vacuum chamber and containment magnets, a shape so incredibly complicated that it had to be designed on a supercomputer at the Max Planck Institute in Germany and welded together by precision computer guided robots. There are 50 magnet coils in here, each containing over a kilometre of superconducting cable weighing 6 tonnes. The idea behind these incredibly intricate twists and turns is to overcome a problem encountered in these standard tokamak donuts. Inside those more simple shapes, the magnetic field is stronger in the centre of the donut and weaker on the outer rim. That imbalance causes particles to drift off course and hit the wall of the containment chamber, and once that happens, your reaction is over. The stellarator's contorted shapes add a twist that forces particles through regions of high and low magnetic fields, so the effects of the two cancel each other out. And that keeps the plasma in place so precisely that the reaction tends to be much more reliable. But fundamentally, both these technologies rely on the brute force of enormous energy inputs to raise temperatures to levels that are about 7 times higher than the centre of the sun. Reaching and maintaining those conditions generally requires more energy than the reaction itself generates. There have been 1 or 2 breakthroughs where a net positive energy result has been achieved, but only very tiny amounts and only for very short periods of time, measured in seconds rather than hours or days. So these machines are still some way off providing our civilization with the ultimate solution to everlasting unlimited energy. And that's where our Australian friends come into the picture. The company, called HB11 Energy, is the culmination of decades of research by Emeritus Professor Heinrich Hohrer of the University of New South Wales. On the 21st of February 2020, the company announced patents in Japan, China and the USA that protect what it claims is a unique solution to the conundrum of nuclear fusion. The company describes the design as a largely empty metal sphere where a modestly sized fuel pellet made up of hydrogen and boron-11 is held in the centre with apertures on different sides for 2 lasers. One laser establishes the magnetic containment field for the plasma, and the second laser triggers what the company call an avalanche fusion chain reactor. The idea of using lasers in nuclear fusion is nothing new. In fact, there's a whole second category of research that sits alongside the magnetic confinement technologies we looked at just now, and that category is called inertial confinement. But as HB11's managing director Dr. Warren Mackenzie clarifies in an interview with Loz Blaine for the tech website New Atlas, we are sidestepping all the scientific challenges that have held fusion energy back for more than half a century. He says that unlike other nuclear fusion technologies that simply aim to produce energy to heat up water to drive steam turbines in exactly the same way as nuclear fission or fossil fuel power stations do today, the HB11 concept will directly generate electricity with no steam turbines required, and they claim their experimental system is already working 1 billion times better than expected. A lot of fusion experiments are using lasers to heat things up to crazy temperatures, says Mackenzie. We're not. We're using the laser to massively accelerate the hydrogen through the boron sample using nonlinear force. He explains that the fusion of the hydrogen and boron creates a couple of helium atoms. Those helium atoms are naked, which means they don't have any electrons. And that lack of electrons is a product of HB11's reaction. It means the helium atoms have a positive charge, which HB11's machine harnesses to create a current that can be used directly. The lasers use a technology called chirped pulse amplification, or CPA, developed in the mid-80s by Donna Strickland and Gérard Moreau of the University of Rochester in New York. The technicalities of that technology are way outside the scope of this video, but essentially it's a way of amplifying tiny laser pulses up to enormous power levels. We're talking petawatts of energy here, which is a lot of zeros. My vacuum cleaner is rated at about 1 kilowatt. 1,000 of these would be a megawatt. 1,000 megawatts is a gigawatt. 1,000 gigawatts is a terawatt, and 1,000 terawatts is a petawatt, which is just a ridiculous amount of energy. Anyway, the development of CPA earned its inventors the 2018 Nobel Prize in Physics, so it was a big breakthrough, and it means that HB11's reactors would be much smaller and simpler than the high temperature fusion generators like tokamak and stellarator. Dr. Mackenzie says that their generators would be compact, clean and safe enough to build in urban environments, with no nuclear waste involved, no superheated stream and no chance of a meltdown. The father of the technology, Professor Heinrich Hohrer, is extremely optimistic about HB11's achievements. He said experiments and simulations on the laser-triggered chain reaction are returning reaction rates 1 billion times higher than predicted. This cascading avalanche of reactions is an essential step toward the ultimate goal of reaping far more energy from the reaction than you put in, which means HB11 stands a high chance of reaching the goal of net energy gain well ahead of the other groups. What's really amazing, said Dr. Mackenzie, is that Heinrich Hohrer envisaged and described this technology way back in the 1970s. It's only possible now because the brand new CPA lasers are capable of doing it. So let's cut to the chase then. When's it going to be ready for commercial scale rollout? Yeah, let's check back with Dr. Mackenzie again. The timeline question is a tricky one, he says. I don't want to be a laughingstock by promising we can deliver something in 10 years and then not getting there. First step, he says, is setting up camp as a company and getting started. First milestone is demonstrating the reactions, which he said should be easy. Second milestone is getting enough reactions to demonstrate an energy gain by counting the amount of helium that comes out of a fuel pellet when we have those two lasers working together. That'll give us all the science we need to engineer a reactor. So the third milestone is bringing that all together and demonstrating a reactor concept that works. So that cliche I mentioned earlier, you know, the one about nuclear fusion always being 20 years away, that one, yeah. Well, it looks like, at least for the time being, that remains the reality. But this new technology is undeniably exciting news. If HB11 succeed, then we could see very small, very cheap industrial units on the outskirts of every town and city in the world, producing unlimited, safe, clean, zero carbon electricity for as long as we need it. Could this be the answer we're looking for? Should we be throwing all our resources at this instead of renewables like solar and wind? As always, I look forward to reading your views on the subject in the comments section below. That's it for this week. These videos are made possible with the help of a group of incredibly generous individuals who support the channel over at Patreon with pledges of $1 or more a month. If you like what we do here and you want to contribute towards getting the message of climate change mitigation and sustainable technology to an ever wider audience, then you can get involved in supporting and influencing the channel through monthly content polls and Patreon forums by visiting www.patreon.com/justhavathink. You can also support the channel for free by subscribing and hitting the like button, which raises our profile with the YouTube search algorithm and gets our message out to more and more people each week. Dead easy to do that. You just need to click down there or on that icon there. And don't forget to hit the bell icon so you get notified about new content. As always, thanks very much for watching. Have a great week if you can, under the current circumstances. And remember to just have a think. See you next week.